Hello everyone, my name is Kirti Amolik, Assistant Professor in Organic Chemistry at RBNB College, Chiral. In the last lecture, we have started the one of the course of the M.Sc. second year Organic Chemistry. It is CHO 352, second section of that it is Asymmetric Synthesis. So asymmetric synthesis, we have seen the introductory part, the important term which are involved in the stereochemistry of the compounds which is related to the asymmetric synthesis. Now it is necessary to design the synthesis in the laboratory that will generate the single enantiomer. So what is our objective? It is to synthesize or to carry out the reaction that will give the high stereoselectivity that will lead to the asymmetric synthesis. So it is also called as the enantioselective reaction. Asymmetric reactions, they are called as also the enantioselective reactions or enantioselectivity. So enantioselectivity refers to the synthesis of single enantiomer as the major product or synthesis of single enantiomer only in given reaction. It is called as the enantioselectivity. So single enantiomer can be obtained only when the reactions has the chiral environment. So in order to carry out or in order to synthesize only single enantiomer, it is our target in the asymmetric synthesis. So for that, the compound first criteria is the compound which is used as the reactant of the substrate. It should be present in the optically pure form or enantiomerically pure form. We know that the compound which are present in the nature or naturally occurring compounds, they are present in the enantiomerically pure form. Only they will exist as the single enantiomer. But when we see the reactions in the chemical laboratory, in that reaction we are getting the product. They are generally the racemic mixture or 50-50% of the enantiomers are synthesized. But in nature, only one enantiomer is synthesized, like key or lock mechanism type of the mechanism is operating in the biological system. So those are generally enzymed catalyst reaction. So this type of reaction we want to carry out under the asymmetric synthesis. So for this we have to introduce the chirality in the reaction. So after introducing the chirality in the reaction, the reagent react at only one phase of the substrate. It should not react with the another phase, so that the reaction becomes the enantioselectivity, shows the enantioselectivity, and we are getting only the single enantiomer. So in this case, generally if racemic mixture is obtained, the traditional methods are given. This racemic mixture is resolved, that is separated. But this process, it requires the more time and one enantiomer will get wasted. And it is very tedious process. So it is important to replace this resolution method. So by accepting the asymmetric synthesis, that is synthesis of the single enantiomer can be designed so that we can avoid the traditional method of the resolution of the racemate or the racemic mixture, because one of the enantiomer will get wasted. So it is not very important or not very useful method. So if we go for the laboratory reaction, for example, if we go for the racemic synthesis instead of asymmetric synthesis, so we have to resolve the racemic mixture. For example, if we see the reaction, that is addition of the hydrogen cyanide or sodium cyanide across the carbonyl group. Here is the example. Benzaldehyde is given. This benzaldehyde is reacted with the hydrogen cyanide. So the cyanide minus negative charge is there and hydrogen having the positive charge. So cyanide minus act as the nucleophile and it attacks the carbonyl group on the both faces of the carbonyl. So when attacks takes place from the both faces, the probability of the attack, it is from the both faces is equal. Therefore, we are getting the 50-50% of the racemic mixture. So in this reaction, we can say this is racemic synthesis because we are getting the racemate here. So sodium cyanide is used in catalytic amount. So cyanide adds to the carbonyl group. So we are getting this type of intermediate is formed. Now this on protonation gives the corresponding product, that is manganonitrile is formed. So manganonitrile is the 1 enantiomer, that is DL pair is present in the equal amount. DL pair means the plus or minus here. So R and S enantiomers, they are formed in the equal amount. So this on protonation, it will give the corresponding cyanohydrin compounds are formed. It is called manganonitrile. Now when cyanide minus ion attacks from the front face or above face, then O minus will get oriented on the below side. So we are getting the S minus manganonitrile compound. S minus manganonitrile compound is obtained. When the cyanide attacks from the below side or the back face of the carbonyl group, then the cyanide minus ion, it is get attached to carbon from the back side, and this OH or O minus becomes beta oriented, O minus, or it is R plus manganonitrile compound is obtained. So there is equal probability of the reaction of the cyanide minus ion on the both faces of the carbonyl group. So this is racemic synthesis. So drawback of this synthesis, we cannot synthesize single enantiomer separately. We are getting the both compounds, so it is not very useful. Again, resolution of these compounds are required, which required the more time, and the process is very tedious, and one enantiomer will get wasted in this process. So this is racemic synthesis. Now next point in the asymmetric synthesis we are going to study is the chiral pool or chiral pool strategy. Now in asymmetric synthesis we are going to synthesize only single enantiomer. So chirality should be introduced in the reaction either in substrate, solvent or the reagent. So we have to design the synthesis that will make the one enantiomer, synthesize the one enantiomer. Now what is this chiral pool? This chiral pool, it is nothing but the simply collection of the molecules which are naturally occurring molecules, and they are present in the enantiomerically pure form, and that can having the similar configuration or the similar structure to that of the substrate, so that they can be introduced or incorporated in the substrate. They are called as the chiral pool. So when these type of molecules are used in the synthesis or asymmetric synthesis, it is called as the chiral pool strategy. So chiral pool, using this chiral pool molecule, the process is very economical because these molecules are easily available, economical, and they can be easily separated and they can be easily taken from the nature. So examples of these chiral pools are the L-amino acids, sugars. These are the basic examples of the chiral pool molecules. Number of sugar molecules are present. D-ribose sugar is there. Natural D sugars, this type of structure is given. So N, number of N. So number of N will get changed. So depending upon the value of N, we are getting the different types of the sugars. These sugars can be used in the asymmetric synthesis, that having the similar configuration to that of substrate. Then amino acids are present. We know that in nature only L amino acid exists. D amino acids are not possible, and D sugar exists, L sugars are not possible. So L amino acids, for example, L amino acid is this general formula RCH, CO2H, NH2. We know that amino acid contains CO2H, carboxylic acid as well as amino group, and amino group is always shown by beta oriented because this having the L amino acid. Now different types of the acids, alpha hydroxy acids are present in the nature. They are also used as the chiral molecules or chiral pool. Next example, it is the S-lactic acid. So S-lactic acid, it having this structure in which carboxylic group is present, alpha position OH group is there, and methyl group is present. So this is a component of the milk. It is present in the milk, lactic acid. So it is also used in the chiral pool strategy. Then D-ribose sugar, it is example, one of the example of the sugar, D-ribose sugar. And S-leucine is the example of the amino acid. So this type of the amino acids and carbohydrate molecule, these are used as the chiral pool. So chiral pool, simply it is the collection of the naturally occurring enantiomerically pure compound that can be easily available, economical, and that can be taken, that having the relative or similar configuration to that of substrate, and that can be incorporated with in the substrate in order to carry out the asymmetric synthesis. So these are the examples. Now let us see some particular chiral pool strategy or the synthesis of some molecule, particular examples that will use as the chiral pool strategy. First example, it is the synthesis of the ipsenol molecule. So ipsenol molecule, it is synthesized from the molecule S-leucine. So we have designed this synthesis already. It is synthesis of the ipsenol. It is synthesized from the S-leucine. We know that the S-leucine is one of the amino acid, it having the S configuration. Why we have used this S-leucine for the synthesis of the ipsenol? Because this ipsenol, it is optically pure compound, single enantiomer. So we have to synthesize the single enantiomer from the enantiomerically pure compound. So we have taken one of the molecule from the chiral pool in the synthesis. So it is called as the chiral pool strategy. Now, why we have taken this S-leucine? Because if we see the structure of the ipsenol, the secondary alcoholic OH group is present on this carbon. This is the chiral center, so it is optically active compound. Now at this chiral center, on the one side there is isobutyl group is present, on the other side here CH2 group followed by 1,3-butadiene structure is present. So these two branches are present on this chiral carbon atom. So we have to synthesize this molecule from the enantiomerically pure compound that having the relative configuration or the relative structure, which are again present in the pure enantiomerically pure form. So if we see the structure of S-leucine, it having the S configuration at this carbon, chiral carbon, NH2 group is present, CO2H group is present, and the side chain is isobutyl group. So again isobutyl group is similar to the isobutyl group which is present in the ipsenol. And next to isobutyl group there is chiral center. So there is again next to isobutyl group there is chiral center. Here at the chiral center OH group is present, and it is another branch. We can incorporate this branch by adding this branch to the molecule, but at this chiral center OH group is present, and at this chiral center the NH2 and CO2 OH group is present. So we have to design, we have to convert this functional group into OH group, and it is possible because we can remove the NH2 group by diazotization reaction, and we can also remove the CO2H. So we can carry out the functional group transformation. So this is due to this similar part and this similar configuration at this chiral center. We have taken one naturally occurring pure, enantiomerically pure compound, it is leucine. So let us see now how we can synthesize this molecule. Now let us start with the leucine. Now the isobutyl group is already present here, so it is necessary to convert NH2 and CO2H group into OH group. So our first objective is to convert NH2 into OH group. So that can be done by diazotization reaction. We know that NH2 can be converted into N2 plus, which is good leaving group, and which on hydrolysis gives the OH. So that will give the required configuration, and further we can generate the corresponding OH group. So at first we have to carry out the diazotization reaction. Nitrous acid is used. HNO2, it is nitrous acid, and it is generated from sodium nitride and HCl. So this nitrous acid reacted with NH2 group, we are getting the N2Cl or salt is formed. So N2 So NH2 group is converted into N2. It can be easily removed here. On the back side, OH group is present, and this OH group having the lone pair on oxygen, it may act as the internal nucleophile. So intramolecular SN2 type of displacement occur. So this OH group attack this carbon from the back side, and this N2 is present on the front side. So it is good leaving group, it can be easily removed. And we are getting the corresponding alpha oriented lactone is obtained, 3-membered lactone is obtained. Now this lactone on hydrolysis